Good evening, class. We are studying chapter 6, trigonometric functions, and the first one deals with angles and their measures. In this chapter, we cover angles and their measures, trigonometric functions, the unit circle approach, properties of trig functions, graph of trig functions, sine, cosine, tangent, cotangent, cosecant, and secant. We are going to look at sinusoidal curves and the concept of a phase shift. That's what we are going to cover in this chapter, in this section. We are going to look at the conversion among various stuff such as degrees, minutes, seconds, and so forth. Length, we're going to look at how we calculate the length of an arc, the area of a sector, conversion between degrees and radians, and linear speed and angular speed of an object. So, with that being the case, we have chapter 5 here, the synopsis of that. We went over chapter 5, composite functions, exponential and log functions. We just had an exam on that. Some properties of logs, it is extremely important for us to know it, so you want to be very comfortable with those. Okay. And so let's go to this section 6.1 and deal with angles and their measures. First, I want to go over stuff that I believe everybody knows from trigonometry. However, we're going to spend a couple of minutes to refresh everyone's memory, and then we're going to move on. Vertex, line and ray, initial side, terminal side, positive, which is counterclockwise. CCW stands for counterclockwise. Okay. A negative, which is CW or clockwise, that's the rotation. And standard position of an angle. So to get started, as you can see, a ray in essence is a half line versus a line that is one-dimensional and continues indefinitely on both sides. If you look at this line, a ray stops at some point. So as you can see, that point, if you happen to have two half lines connected at a point, that point is considered the vertex. Again, all of this is posted, class. I just want you to see if you can remember this stuff. Everything is posted. So I don't want you to really waste your time writing. Just pay attention. So for example, when we look at this angle, okay, vertex, okay, when the two rays come together, the intersection of the two, initial side and then terminal side, okay. Look at the way we are looking at alpha, it's counterclockwise rotation, which is considered a positive angle, okay. Now again, initial side, okay, clockwise rotation, it's a negative angle. Okay, so positive versus negative. It's important to see that there are angles that may have the same terminal side known as coterminal angles. Okay, so let me, what happened, sorry. All right, and so as I was mentioning, coterminal. Coterminal refers to angles that they have the same terminal side, obviously the same initial side as well. And so now we have a standard position. Standard position means the initial side is along the positive x-axis. Positive x-axis. If you look at part A, it's positive. If you look at part B, it's negative. Nevertheless, look at the initial side and its location. All right. I hope this page is fairly straightforward, class. Okay. All right. Now, we're going to continue with definitions. Quadrant and quadrantal angles, right angle, straight angle, and so forth. Okay. So as far as the quadrants are concerned, when we look at this example, the angle, if you look at the terminal side is in quadrant 2, everybody remembers quadrant. One, two, quadrant 3, quadrant 4, 1, 2, 3, 4. In that order. So because theta lies in quadrant 2, meaning the terminal side, it's in that quadrant. So there are 4 quadrants. This is in quadrant 4. Okay. And by the way, this is in a negative rotation. This would be the positive rotation. So those 2 angles are considered coterminal. Okay. Now, a quadrantal angle refers to the angle that the terminal side is on one of the axes. For example, right now the way this is, some of you obviously remember this is 3 pi over 2, okay? If it ended up here, for example, would be pi over 2. Here would be pi or 180 degrees, known as straight angle. And you may go the whole rotation 2 pi radians or 360-degree angles. So as you can see, this is referring to what I was just mentioning, a complete revolution, okay, means you're dealing with 360 degrees or 2 pi radians. A right angle, everybody knows it's supposed to be 90 degrees or pi over 2. And straight angle is 180 degrees or pi radians or half of revolution, however you want to put that, that's fine. So again, refreshing everyone's memory about some basic stuff that we have seen in trig. I'm gonna assume we are ready to move on, everybody. All right. Okay, so in this example, we want to draw some basic angles. 45 degrees, remember, the way it's going to work is very simple. we are going to start with an initial side along the positive x-axis. So 45 degrees, we do counterclockwise to end up with a terminal side, so we should have no problem drawing that. This is a rough sketch. You may do the rough sketch, and that's good. Of course, a question like this, you just have to recognize the angle. Negative 90 degrees start with the same initial side, but this time we go on the negative side, which means we end up with right here. If we go on the positive side, class, it's 270 degrees, okay? Or 3 pi over 2. So if let me use a different color here. If we go this way, this is 270 degrees, okay? Or 3 pi over 2. Okay. 225 degrees, 405 degrees. Let's give everybody a moment to think about that. If you were to draw those, how would you do that? So I want to make sure everybody can picture that. Okay. Remember, in the case of 225 degrees, when we start with the initial side, this is larger than 180 degrees. Therefore, it goes half a revolution, and then we add another 45 degrees. So it looks something like that, okay? As far as 405 is concerned, 405 degrees. It's larger than 360 degrees, okay? As 225, you should know it's 180. Plus 45, okay? And so if, let's just, if you know this is 180, then you go further by 45 degrees, halfway between 180 and 270, okay? And remember, this is 270. So having said that, as far as 405 is concerned, 405 is larger than 360 degrees. Again, it happened to be the same amount, so that means a complete revolution. And then we add to it 45 degrees, which puts us in the first quadrant. Okay, so I don't think anybody is having any problem with these questions, okay? Just refreshing everyone's memory, and so we can move on. All right. This is example 1. We looked at how to draw angles in standard position. All right. Now we want to convert between decimals and degrees, minutes, seconds, and so forth. Now, as far as definition is concerned, everybody remembers that a complete revolution is considered to be 360 degrees. 1 degree is defined as 60 minutes. 60 minutes. So I hope everybody knows when we look at this notation. Okay, 60 minutes. And 1 minute is 60 seconds. All right, so let's see how we do the conversion. Part A says, okay, we have 40 degrees, 12 minutes, and 5 seconds. we want to put it in decimal. For example, the idea is that we want to see 40 point what degrees. That's the question, okay? So here's the way the transformation takes place. We know that 1 degree is 60 minutes, okay? So it is the same as saying that 1 minute is 1 over 60 degrees. And 1 minute is 60 seconds. So a second is 1 over 60 times minutes, and 1 over 60 times 1 over 60 makes it 1 over 3,600 seconds. So I think it's clear to everybody. So with that being the case, 1 minute is 1 over 60, and 1 second is 1 over 60 times 1 over 60, which is 1 over 3,600, okay? Okay, so that's fairly straightforward. And so now we're going to keep the 40 degrees intact. The 12 minutes becomes 12 times 1 over 60. And 5 seconds becomes 5 seconds. I'm sorry, 1 over 3, 3,600. So times 1 over 3,600. Okay. And you use a calculator with a bunch of decimals, you end up with 40.2014 degrees. This is how you go from degrees to decimals. Vice versa. Now we want to convert 78 degrees, 78.562 degrees into degrees, minutes, and seconds, in which case 78 degrees remains unchanged. It is 0.562 that needs to be changed. Okay, so here's what we do. First, we change that to minutes. Remember, 1 degree is 60 minutes. So whatever the amount of degree, you have to multiply it by 60. So 78 doesn't change. 0.562 0.562 gets multiplied by 60, and using a calculator, it gives us 78 degrees plus 33.72 minutes. Now, if the question was put it in degrees and minutes, we would be done. But we don't want it that way. We want it degrees, minutes, and seconds. So 0.72 minutes has to be changed to seconds. And remember, 1 minute is 60 seconds. You got to multiply the fractional portion by 60. And we get 78 degrees plus 33 minutes plus 0.72 times 60 seconds. And generally speaking, when we represent it in this fashion, we don't want decimals. So we rewrite this as 78 degrees, 33 minutes, and 43 seconds.
So we round.
Any questions, class? Go ahead.
We round if there is a leftover, like 43.
Yes, yes. We round. If it was 43 point, let's say 7, we would change it to 44. And the reason being because seconds is extremely small, okay? Generally speaking, we do that just for the sake of argument. If you were doing an exam and it was a paper, I wouldn't have any problem if you left it at 43.2 seconds. As you do it with MOM, my open math, make sure you follow them so you get 4 credit. All right, sounds good. Any questions? All right, we're going to move on. I'm going to assume we are okay with this class.
Yeah.
Yeah.
Perfect.
Yes.
All right. Now let's go with radians. Radian has a specific definition. Everybody knows that 2 pi radians, okay, is 360 degrees. But what is the definition of that? Okay, and that's what we want to discuss. Okay, it is the measure of central angle whose arc length is equal to the radius. And that ends up being about 57.3 degrees. Now, equal to 57.3 degrees is not the definition, class. It ends up being equal to that. The definition is a measure of central angle, okay, that covers an arc which is equal to the radius in length, okay? So what it means that it doesn't matter how large the radius is, okay? You could come up with an arc having an equal, length, and that would be the same measurement in radian. So 1 radian is equal to the arc length. So if you look at, for example, the small circle has a radius 1. The arc length. So for small one, this is the, let me use a different color class. This is, no, that didn't work either. This is the arc length. So the arc length here versus the arc length here. We are not saying the arc lengths are the same. They are not, okay? Actually, the arc length depends on the length of the R. But what we are saying that the measure of the angle, they're identical. All right. So let's look at the arc length and how we find it. Everybody remembers the circumference of a circle is equal to 2 pi r. So using that concept, we want to find the arc length, which is very simple, okay? How do we find the arc length? Using the fact that circumference is 2 pi r, okay? So you want to look at this one, okay? We know that C is 2 pi r, okay? And what is 2 pi? 2 pi is the angle which is a complete revolution. When you cover the whole circle, starting from any point, you go a complete revolution, you cover the circumference. So 2 pi can be represented by theta. So C equals R theta in essence, where theta is 2 pi for the circumference. If this is the case, then we call it S equals R theta. If theta is 2 pi, it's the circumference of a circle. If it's not, we call it the arc length. S equals R theta. So to recap this quickly, in essence, arc length is portion of a circumference, everybody. Arc length is a portion of a circumference of a circle. Circumference covers a whole revolution, 2 pi radians, and therefore the circumference of 2 pi r corresponds to arc length S equals R theta. So here's a very simple example. We want to find the length of the arc of a circle whose radius is 4 meters, okay? The central angle must be in radians, and that's 0.5. So using S equals R theta, just replace the R with 4, theta with 0.5, and you have the answer. The arc length of a circle whose radius is 4 meters, whose central angle is only 0.5 radians, I should say, it's 2 meters. 2 meters. Okay. Sounds good, everybody? Any questions?
No.
All right, we got to move on. So, the formula we covered here, S equals R theta. That's all we need to remember from this page. All right, let's see how the conversion takes place. First, remember, 1 revolution is 2 pi radians, or 360 degrees. 2 pi radians, or 360 degrees. Half of that, half of the revolution, is pi radians, or 180 degrees, or 180 degrees. So if that is the case, 1 degree would be pi over 180 radians, okay? And 1 radian is 180 over pi degrees. Here's how I'm gonna put the two together, so I hope it will be easy to remember. Take a look at the formula at the top. 180 degree corresponds to pi radians. Everybody knows that. So at top of 180, you put D standing for the degrees. At top of pi, you put R standing for the radians. So what happens now? Any of them given, you put it in. If the degrees given, let's say it's 30 degrees, replace the D with 30. Cross product will give you R. If R is given, let's say R is pi over 6. Cross product will give you the measure in degrees. So instead of going over the rest of this, just remember this formula, class. This is a very easy formula to remember because everybody knows 180 equals pi. Okay, instead of saying 1 degree is pi over 180, 1 radian is 180 over pi, just remember this formula. I have put those two concepts together for you. Sounds good? So now, by the way, this S equals R theta is shown here also, class. And S equals R theta. Theta is replaced with 2 pi, gives you the arc length that covers a whole revolution, which is called the circumference. Now, there are some common angles, and I believe most everybody remembers them from before. For example, 0 degree and 0 radian obviously are the same. 30 degrees is pi over 6. Here's an example that I can't believe anybody not remembering that. So these are common ones, okay, that you really need to know. At the very least, the first row, everybody should know. If for some reason you don't know the bottom row, I understand. But the top row, it's so common that you really should know. Okay, class? All right. We know those that, conversion shouldn't be a big deal for that, but let's quickly show a conversion here, class, okay, just for the sake of argument. We already know this page. Those are common angles. But for example, 30 degrees, 120 minus 6104. And I don't want to really spend too much time on this page, okay? Because basically, you can use the formula that you have up there, okay? You can either say, for example, 30 degrees is 30 times pi radian over 180, and it gives you pi over 6. You already know the answer. Or the method that I went over, you can say, okay, let me write this, 180 pi, okay. Now the top is D and R, okay. So what is given? D. So you write it. What is missing? R. So you write R. Now if you do the cross product, okay, you get 30 pi equals 180 R. And R is 30 pi divided by 180. And as you can see, is the same as pi over 6. Again, I don't want to spend too much time on this stuff, class. It's very straightforward. So I would use the top right formula in blue. It makes life easier. The rest of it, I'm going to quickly show you. Okay. So I wouldn't worry about that. The only thing which is not a, and by the way, A, B, and C are common arcs. You should know them. Okay. But part D, you have to work it out. So I would do it this way, or the method I showed you. When you finish it off is 1.815 radians, okay? Again, you can look at it later on. Going back, again, you're looking at some of them that are common. For example, negative pi over 2. Everybody knows pi over 2 is 90 degrees. So negative pi over 2 is negative 90. So that shouldn't be a big deal. However, you can go through the process that way, or again, let me just use the formula D over 180. Let me just show you how you would get the D over 180, you know, if you were to do the math in this manner. Okay, R, which is negative pi over 2 over pi. The pi's cancel each other, and you can figure out what you end up, okay? And so that shouldn't be a big deal at all. So you end up with negative 90 degrees. 5 pi over 6, okay? Again, remember pi over 6 is 30 degrees, so 5 of them is 150 degrees. Or you can go, this is the method that I was just explaining. Or you can go over this process, find 150 degrees. What I want to do, I want to give everybody a moment. See if you can quickly figure out the 5 radians, class, and we take it from there. All right. Again, you can go through this process and come up with the answer, or you can write it as D over 180 equals R, we know it to be 5 over pi, and you do the cross product. Pi times D, and then 5 times 180. So you can say pi times D is 5 times 180. You divide both sides by pi using a calculator. Pi is 3.14159. and it gives you an approximation of 286.48 degrees. All right, I wouldn't worry about this. I'm gonna assume we are in good shape. Any questions, everybody? So
No.
conversion shouldn't be a big deal. So I'm gonna move on. Okay. Could somebody be kind enough to read this question for the class, please?
The latitude of a location L is the angle formed by a ray drawn from the center of the Earth to the equator and a ray drawn from the center of the Earth to L. Glasgow, Montana is due north of Albuquerque, New Mexico. Find the distance between Glasgow, approximately 48.15 or 48 degrees 9 seconds.
Yeah.
North latitude, and Albuquerque is approximately 35.083 degrees or 35 degrees 5 seconds north latitude. Assume the Earth's radius.
I'm sorry, 35 degrees 5 minutes. My apologies.
Oh, minutes. Okay.
Minutes. Okay.
35 degrees
Prime.
and 5
One
minutes.
prime. Okay. If there is one prime, it's minutes. If double prime, it's seconds. Go ahead, please.
Okay. Thank you. Assume the Earth's
Thanks.
radius is 3,960 miles.
Thanks. Sometimes to make the approximation easier, they use 4,000 miles, okay, as far as the radius of the Earth is concerned. So I hope you see the concept, okay? And the concept is something similar to this class, okay? So they have it, you know, they give us the latitude, and the difference between the two angles is the angle between the two cities. So the central angle between the two cities is one minus the other. And the assumption is everybody can do the math. It's not a big deal, okay? Now, we want to use S equals R theta, okay, class, to find that distance, okay? The arc length is the distance. So, in other words, let me see if I can use a different color. We are interested in finding this arc length. Do you see that, everybody? This arc length, okay? And this arc length is S equals R theta. And anytime you want to use that, theta must be in radians. So right away, you change the degrees to radians. That shouldn't be a big deal to anyone. And all of it is an approximation. It's a very good approximation. I want you to know that. But it is an approximation. So S equals R theta. R is 3960 miles. Their product gives us about 903 miles. Again, it's not a bad idea to use more decimals, okay? 903 is fine. Maybe a couple more decimals, that's okay too. Again, as you do your online assignments or exam, pay attention to the number of decimals that you were asked to use. So this is I really love the word problems we have here. It's such applicable questions, is unbelievable, okay? So I hope everybody is okay with that and see, you know, how this stuff is used, okay? All right, any questions? Everybody okay with that?
Yeah,
So
okay.
perfect. So we discussed the arc length. Let's look at the area of that piece, that wedge, which is called a sector. So now, how do we find the area of a sector? We look at the formula that we have for the area of a circle, okay? We know the area of a circle is equal to pi r squared. Everybody knows that, right? A equals pi r squared. Now we can see that a whole revolution is 2 pi. So we are going to represent the pi as half of 2 pi. Why do we do that? Because this is your angle theta. So if you cover the whole circle, the angle that you cover is a complete revolution of 2 pi radians. Therefore, we're going to say the area is equal to 1/2 theta times r squared, or simply 1/2 r squared theta. Does that make sense to everybody? Is everybody fine with that? Okay.
Yes.
So this is the justification as to how we arrive at it. In fact, if you ever forget, if you do use this justification, it comes back to you. So I'm going to repeat that so hopefully everybody remembers. To come up with the area of a sector, you use the area of a circle and compare. To come up with the arc length, you use the circumference of a circle and you compare. Sounds good? Everybody?
One more time.
In order to find the area of a sector, compare it to the area of a circle and it comes to you. The formula comes back to you. In order to find an arc length, in case you forgot the formula, S equals r theta, compare it to a circumference. So I'm going to quickly write it here so you see what I mean by that. See? The one we just covered.
A equals pi r.
You know that circumference is 2 pi r, right? So what is arc length? 2 pi is the same as what? Theta, isn't it? So theta times r, which is r theta in essence. So just a matter of comparing it with a circle, you can figure it out. In any event, here's a simple example. We want to find the area of the sector, okay, with a radius of 5 feet and a central angle of 60 degrees. Okay, now we are looking at the formula at top, so I want to quickly go over that actually. Okay, the area is 1/2 r squared theta, where r is given as 5 feet and theta is given as 60 degrees. So can we use 60 just the way it is, class? Can we use 60 just the way it is?
No, you have to convert it to radians.
And perfect. And we all know by now, I believe, that it's pi over 3. We can easily calculate it. And the answer, of course, is in feet, okay? Because the radius was in feet. All right. So now what about this case? The radius is 2 feet. The angle is 30 degrees. And it's a very simple calculation, class. So go ahead and do that quickly. What do you get, class? Excuse me. And so you plug in 1/2 r squared, which is 2 squared times pi over 6, okay? And you have pi over 3 feet. By the way, class, this is an exact answer, okay? In feet. And then using a bunch of decimals, you get an approximation. All right. So we covered area of a sector and arc length. So we are going to move on to the next topic. Everybody remembers D equals RT. Okay, D is the distance, R is the rate, and T is the time. and by r we normally means the speed or velocity. So distance divided by time, distance divided by time, in which case a linear speed is total distance over total time. If you're going around a circle, the distance would be the amount of arc length you're going to cover, which is s, divided by amount of time, which is t. This is known as linear speed. Linear speed, everybody, okay? Linear speed. Now, what about angular speed? Angular speed has the same type of definition. Instead of saying total distance over total time, it's angular. So we say total angle over total time. So if that is the case, the total angle we cover is theta over the time is theta over t. Now, it's extremely important to understand the relationship between the two. Regardless of the radius and the size of the radius, okay, if we cover the same angle, our angular speed remains the same. However, as the radius changes, the linear speed changes. In fact, as you get further away from the center of the circle, it seems to go faster. Everybody knows what I'm talking about, right? Here's the reason. S, we can replace it with r theta. Everybody knows that, right? S is the same as r theta, right, class? So replace the S with r theta. You get r theta over t, or r times theta over t. And so V equals r omega. Omega represents the angular speed, everybody. V equals r omega. V equals r omega, angular speed. Okay, angular speed. All right, I'm going to move on and look at some examples. I have a lot of examples here, and many of them we won't have time for it, so I probably leave it there for you to discover it on your own and see how things go, but we want to cover quite a few to be on the safe side. Before we move on, everybody okay? Any questions, class? All right. In the meantime, I appreciate if someone, keep an eye on our chat, and if somebody has a question, please bring it up. All right, so here's a simple example. So first at top in blue, I put the formulas we just discussed. Omega is theta over t, okay? And V is S over t or R omega. By the way, omega is also equal to 2 pi times RPM. And I'm assuming everybody remembers RPM stands for revolutions per minute. It could be RPS, revolution per second, or RPH. So I don't want to have to write the whole thing again. Revolution per and then unit of time, whatever it may be. So here's an example. A child is spinning a rope at the end of a 3-foot rope, and the rate is 160 revolutions per minute. Okay, that means in 1 minute, it covers 160 revolutions, complete, revolution in that circular motion. We want to find the linear speed when it's released, okay? So we know that V equals R omega, okay? But what is omega, okay? Angular velocity, if RPM is given, then it's 2 pi times that, okay? And so we know RPM is 160. So omega is 2 pi times RPM, revolutions per minute. And the units becomes radians per unit of time, everybody. When you multiply by 2 pi, the units become radians per minute. And so now it's 2 pi times 160, it's 320 pi radians per minute, okay? Now, for now, you can keep it as that, okay? If you want to use pi as 3.14159 and find the approximation, so be it. V equals R omega. V equals R omega, where R is simply 3. And so when we multiply, we get 960 pi. Now, 960 pi is about 3,016 feet per minute, okay, class? And so it's really a good practice to use more decimals. I want everybody to know that, okay? But in any event, that's okay if we did it like so, okay? I just want to make sure you know that it's a good practice to have a lot of decimals in case you have any doubts, okay, class? All right, so going back to this, now the next step is, okay, find the linear speed of the rock when it's released. If you left it as that, it's absolutely fine. I want you to know that. But normally, we don't use that unit. And again, this question given doesn't ask for anything, you're done. But how do we change this to miles per hour? Okay, we know 1 hour is 60 minutes. And we know 1 mile is 5,280 feet. So we use the fact in this fashion. Okay, class? So I want to make sure everybody understands how we use that. Remember, class? One mile is 5,280 feet. Okay, so whether you say 1 mile divided by 5,280 feet or 5,280 feet divided by 1 mile, it's a unit. Same thing, whether you say 1 hour over 60 minutes or 60 minutes over 1 hour, it gives you 1 unit. But how do you write it? It depends how you want the final answer to look like, okay? Notice what happens here. Regardless of the numbers, okay? First you look at feet, they cancel each other, okay? Minutes, they cancel each other. And there is nothing except mile in the numerator, hour in the denominator. So you're looking at miles per hour. So you say 3,016 times 60 divided by 5280, and it gives you a rough estimate. Again, I highly recommend you use more decimals, everybody, okay? But for now, this is good enough. So let's look at one more example, and then we take a break. Before we do so, is everybody okay and clear on this one? Any questions, class?
No.
All right. Again, please understand when we go over these questions, you really have to spend some time, you know, going over them and get comfortable with them. So I'm going to go over the next one. Could somebody read this question for us, please?
An object is traveling around a circle with a radius of 8 inches. If in 40 seconds a central angle of 1/3 radian is swept out, what are the linear and angular speeds of the object?
Perfect. Thank you so much. Okay. So we have the radius. Okay. We have the time. So radius is 8 inches. Time is 40 seconds. And the central angle, theta. So R is 8. T is 40. Theta is 1/3 radians. So we want to look at the linear and angular speed. Omega has a simple definition, theta divided by t, so plug in. And it's 1/120, 0.008 radians per second. V equals R omega. We just have omega. R was given as 8. Their product is the answer, 1/15, or roughly 0.067. And don't forget the units, okay? Inches per second. All right, class, welcome back. Let's go over this question. The minute hand of a clock is 6 inches long. We want to see how far its tip move in 15 minutes, 25 minutes, and we are going to use 2 decimals. All right, so with that being the case, let's see what's given and what we need to come up with. We know that the minute hand is 6 inches long, and we're going to use the formulas. We are interested in finding how much it moves over the course of 15 minutes, okay? So that means this will help us find the, okay, now. Okay, let me use a card. So this will be referring to the angle that we need, and this is the radius, okay? So radius. Now, 15 minutes, we know a whole revolution consists of 60 minutes. So it's 1/4 of a revolution, 1/4 of 2 pi, and therefore we have a radian measure of pi/2. S equals R theta. So 6 times pi/2, precisely 3 pi, roughly 9.42 inches. So let's give everybody a moment. So if you can calculate the second part on your own, let's give everybody a moment. I'm going to pause the recording. So we need to calculate the theta. In this case, it's 25/60 times the revolution. A revolution means 2 pi, and that is the result, 5 pi/6. S equals R theta is used again. And it's 5 pi, precisely, roughly 15.71. The units will be the units of the radius. Okay, the units of the radius, everybody. Sounds good? Any questions, class? All right, we're going to move on. So we're going to look at a few interesting examples. We're going to go through them fairly fast because, again, the question is posted. I just want to go through the process of how we arrive at the answer. So with that being the case, you should be ready for the next one. This is a fairly long section. All right, here's another example. So a 40-inch pendulum. So right away, we realize what this is. So in 20 degrees each second, how far does its tip move each second? So this means obviously this is the radians. Okay. So 20 degrees has to be changed to a radian. So I'm going to assume everybody will use the proper method to change it, and I'm going to refresh your memory. This is the fastest way. Replace the D with 20 degrees, find the missing R. That's all there is to it. So pi over 9 radians. So S is R theta. Here's the formula. And it's 40 times pi over 9, 40 pi over 9 precisely, using a pi of roughly 3.14159. We can come up with the answer of 13.96 inches. Okay, this is the theta in degrees. Sounds good? All right. We're going to go to the next example. Could somebody read the question for us, please?
A water sprinkler is to cover a field of 100 square yards in the shape of a sector of a circle of radius 5 yards. What is the angle needed for this rotation at 2 decimal places?
Thank you so much. So this is the area of a sector. And that's the formula. So we need the radius. So we have A equals 100 yards squared with the radius of 5 yards. We have those two. Okay. And we have the formula 1/2 r squared theta. We replace the A with 100. We replace the R with 15, and we find the theta. Theta is 8 over 9 radians, okay? And if we want to know it in degrees, remember we use the formula that I mentioned. What is missing is the D. What is R? 8 over 9. Cross product will result in D being 180 times 8 over 9. Nine and 180 cancel each other. 20 times 8 is 160 divided by pi and bunch of decimals. We get to 50.93 degrees. Sounds good. By the way, the the graph, the picture is supposed to show you the general concept, but the angle needs to be calculated. The angle that it indicates obviously is larger than pi over 2 90 degrees, but that's not the case when we do the calculation. All right, here's the next one, everybody.
Can you hold on just one quick second? Just one quick
Sure.
second. Just take in something real quick. Okay, go ahead. Thank you.
Okay. Could somebody read this question for us, please?
A windshield wiper's arm and its blade are 30 inches long. If the blade is 24 inches long and the wiper sweeps about an angle of 125 degrees, how much window area can it claim?
Thank you so much. Okay, so first, it is important to understand what's going on here. So we want to use the area of a sector, which is 1/2 r squared theta. So this is the formula we need, but it's important to know what we are dealing with. Arm and blade gives us one radius, which is long, 30 inches, okay? But the blade is only 24, which means we have to really calculate A equals 1/2 r squared for both of them and look at the difference, and this is the theta, okay? So it's important to understand what we want. So if you look at the shape, okay, we understand the total area using the long arm and blade together as 30-inch long is the blue area. But we are interested in what the blade does, okay? So we have to look at their difference, okay, class? So one of them is 30, one of them is 24. So the long, okay, the longer radius is 30. The smaller one is the difference between the two, okay? So we want the area of a sector, the total area of the blue, if you will, minus the total area of the gray color, okay? So R1 is 30, R2 is the difference between the two. I can't really emphasize this enough, okay? I should, okay, the order here is not right, so I'm gonna quickly show you what I have in mind. R1, everybody, is 30, which is this distance. Let me see if I use a different color, it's easier to see. So this distance is R1, and it creates the total area, okay, using R1 equals 30. But we want to use, let me use a different color. And this is the smaller one, R2, where R2 is 30 minus 24, the difference of 6. So we can calculate the total area and subtract the gray area, and that gives us the answer. Now, 125 degrees, we can calculate using the process, and it becomes 25 pi over 36 class. In other words, using d over 180 is pi over r, and replace the d with 125 degrees. 125 degrees. It results in 25 pi over 36. So we can calculate this, okay, and subtract from it the gray area. This is the total area, class. Total. And this is the one in gray. This portion. And so the difference, this is exact. You replace the pi, and by the way, that's the given that it should have come up in the first place. R1 is 30, R2 is the difference between the two. Theta is 125 degrees. We should have no problem changing it to a 25 pi over 36 radian easily. And that becomes 300 pi precisely. And bunch of decimals, we end up with 942.48 square inches. All right. Any questions, class? Okay, we're going to go to the next one. An object is traveling around the circle of radius 2 meters. So that's the radius. It travels 5 meters. That's S. Over the course of 20 seconds. That's 20. So now V equals S over T, total distance covered, divided by total time, and it gives us 1/4 units of the numerator over the units of the denominator. So 1/4 meters per second. We want to find angular velocity. V equals R omega. The missing one is omega. Everything else is given. V is given, R is given. So 1/4 over 2 is 1/8. That means 1/8 of radians per second. Okay.
Yeah.
All right. We want to go over the next question, class. All right. Here's the next one. Can I ask someone to be kind enough to read the question for us, please?
A centrifugal force ride, similar to the gravitron on amusement ride, spins at 22 revolutions per minute. If the diameter of the ride is 12 meters, what is the linear speed of the passengers in kilometers per hour?
Thank you so much. All right, let's see what's given. 22 revolutions per minute. That is the RPM, everybody. RPM is 22, okay? Radius is half of this. So those are the given. Radius is 12 over 2, or 6 meters. And RPM is 22, okay? So omega is 2 pi RPM. We have it up there. Omega is theta over T, or 2 pi times RPM. So 2 pi times 22 results in 44 pi radians per unit of time, which is per minute. V equals R omega. V equals R omega. R is given, omega is found. Here's the answer. Now, the thing we want to pay attention to is that we're done, except we want to write them in what? Oh, doesn't work. I want to show you.
You need to write it in kilometers over hour.
Kilometers per hour, exactly. Okay, I can't write. Okay, let's see. Something happened here with my pen. I can't write. Anyways, let's finish that and then I'll see if we need to do something. So 264 pi meters per minute. We want to write it in kilometers. So meters, everybody knows 1 kilometer is 1,000 meters. And minutes, then 1 hour is 60 minutes. So we use the following format: 1 kilometer per 1,000 meters, 60 minutes per 1 hour. So we end up with the units of interest.
So we cross cancel the repeating units, which would be meters in this case, and just multiply across, and then we'll get the answer.
Yes, as always, you know, this is how we deal with the units. I'm sorry, I'm trying to figure out why my pen stopped. It just, hold on. So the way we write the units, class, remember, the idea is to end up with kilometers per hour. Okay, so the kilometer must be at top in the numerator and hours in the denominator. So this should be what we want to end up with eventually. I highly recommend, when you want to figure out how to write that, first write the units that you want to end up with. Okay, so this is what you want to have at the end. Of course, your handwriting is much better. I know that, so you know, don't look at my handwriting. So there is a meters here. You want to get rid of the meters. So that's why the meters is sitting in the denominator. Then you have, let me use a different color, minutes down here. So the minutes should go up there for it to go away. So I hope everybody can see how we take care of the units. That sounds good? Any questions, class? All right. Let's go to the next question. Could somebody read this question for us, please?
Yeah. A DVD drive has a maximum speed of 7,200 RPM. If a DVD has a diameter of 12 centimeters, what is the linear speed in kilometers per hour of a 0.5 centimeters from the disk center if it is spinning at a rate of 5,400 RPM?
Thank you so much. Okay. So what we have here is 54. See, the one that we are interested in, a point of 5 centimeters from the disk. Okay. Okay. The 7,200 is the maximum rate. Okay. And that's fine and dandy. Okay. And that's not what we are going to use. And 12 centimeters is also, so I want to make sure, let me just, we have 12 and 7,200. Those are some information, but they do not enter into our calculation. Why not? Because at this point, 5 centimeters from the disk center, this is the radius we are interested in. Is everybody clear what we mean by that? And the RPM, that's the maximum RPM of 7,200. But at this moment that we are interested in calculating, we are dealing with 5,400 RPM. So it's important to see the given is not the top portion that we are interested in. The given is 5 centimeters as the radius, RPM is 5,400, that's 7,212. Both of them are good information to have. They do not enter the calculation. Okay, so with that being the case, RPM, that means omega is 2 pi times RPM, okay? So 10,800 pi radians per minute. V equals R omega. V equals R omega. You replace the R with 5, and then times the omega you just found. Now, pay attention to the units. Now we end up with centimeters per minute. All right? Now, we can leave it as that if we haven't been asked to change it. But normally we don't represent it in this format. Let's give everybody a moment to figure out, okay, how we would use the transformation of units to get to, let's say, 2 kilometers per hour. And all you have to do, write it in this form, and then see how we can get rid of the minute in the denominator, centimeters in the numerator. Okay? And so that shouldn't be a problem. By the way, I'm going to assume everybody knows 1 kilometer is 1,000 meters, and 1 meter is 100 centimeters. Sounds good, everybody?
Okay.
Yes.
See if you can figure it out. All right, so we write centimeters per minute in a fractional format. And again, we want to make it look like kilometers per hour at the end. Okay, so 1 meter is 100 centimeters. One of them has to go at top. Remember, you want to get rid of the centimeters, so centimeter, 100 centimeters goes to the bottom, see, because you want to get rid of this. Now, meters is at top. We want to get rid of this. Okay, and now you have hours. 1 hour is 60 minutes. Which one is going at top? You have to pay attention to that accordingly. And since minutes in the denominator here has to be in the numerator, they cancel each other. Now you just multiply a bunch of numbers, divide by a bunch of numbers, and you end up with 101.8 kilometers per hour. That means it's about 70 miles per hour, roughly, okay? Sounds good, everybody?
Yeah.
Yes.
I'd like to move on to the next question. Could somebody read this one for us, please?
The radius of each wheel of a car is 15 inches. If the wheels are turning at the rate of 3 RPS, how fast is the car moving? Express your answer in inches per second and in miles per hour.
Thank you so much. Let's see what's given. Obviously, the radius, 15 inches, okay, and RPS, revolutions per second. So those are the given. RPS stands for revolutions per second, revolution per second, this S, okay. Stands for second, revolution per second. Now, the same omega. Omega was 2 pi times RPM. So it's omega is equal to 2 pi times RPS. So the units Instead of being radians per minute, now it's radians per second. Okay, so one more time. 2 pi times RPM. That's how we got omega. Okay, this is the formula. Now, instead of RPM, we use RPS. So what happens? The units, instead of being per minute, is per second. End of this story. All right. So with that being the case, the V formula now, it's R omega. R omega. So we replace the R with number 15. So 15 times 6 pi is 90 pi inches per second. That's the answer. Now we are going to change the units to miles per hour. And I hope everybody remembers a mile is roughly 5,280 feet. So again, I want to give everybody a moment. Quickly see if you can do this transformation. In other words, here's what you want to do. I highly recommend you write it in this fashion. You have inches per second. The final result must be what? Miles per hour. That means whatever you do, the top should become miles, the bottom must be hours. So for example, just for the sake of argument, you can see the relationship between hours and second and inches and miles. Remember what you need to do. And of course, everybody remembers 1 foot is 12 inches, right? So let's see what you can come up with.
Yeah, that's what.
Okay, this is question number 15. This answer is wrong. That's what you say. So what did you get?
10.18.
Oh, thank
10
God.
point what?
18.
18 kilometers
Yes.
per hour.
Just
Is
off
that
by-
what everybody can see? Everybody got that?
Yeah.
Yes.
10.18, am I right, class? So, okay, so I must have messed up the decimal. My apologies. So 10.18, wow. All right, I really
Gotta make
appreciate it.
sure
So,
so we're not going crazy.
believe me, you know, I've been going crazy with all this. You know, I got to put the PowerPoints together for you. I have to make changes and trust me, it's been crazy. So, but you're right. I'm glad that you are paying attention to that, and I thank everybody. Excellent class. We're gonna move on. That sounds good.
I know I kind of feel like discouraged from saying this, but that's not the answer that I got. I got
Okay,
32.4.
I'll tell you what. Why don't you give me your answer?
I got 32.4. I just input this information in my calculator. 5,400 times 1 over 100 times 1 over 1,000 times 60.
It's
And
54,000.
What about the pi?
Oh, 54,000?
Yeah,
Yeah,
so
that's,
initially I got
yeah, that's what I put
3.24,
in.
but then you got to multiply the pi. That's how he got the 10.
Oh, okay. Yeah, that's right. Okay.
So we're okay?
Yeah, never mind. I'm sorry.
Sure. No, I appreciate that. This is good. This is really good. This is a healthy discussion, okay? So 54,000 times pi times 60 divided by 100,000 class. Okay, so let me write that actually. 54,000, okay, pi times 60 divided by 100,000. This is the number we should calculate, and we get 10.18, correct, everybody?
Yes.
Yeah.
Excellent. Thank you so much. So let's move on. So we did this, and we came this far. Okay, and now we are going to make the transformation such that it becomes miles per hour. Notice they cancel each other. Different color. Okay. Seconds. By the way, 1 hour is 60 minutes, a minute is 60 seconds, and it's 60 times 60, 3,600 seconds. And also feet, those cancel each other, and we get to the answer in miles per hour. Is this correct, class? All right.
Yes.
Perfect. So again, most of the time we want to use more decimals, but that's fine. There are a lot of approximations here. Even 5,280, even pi, I mean, is 3.14159, and so that's an approximation. All right, the rest of them are fine. All right, we're gonna go look at the next example. Is everybody okay with this? Okay, we're done, class. Let's go to the next one. Could somebody read this question for us?
The mean distance of Earth from the Sun is 9.29 times 10 to the power of 7 miles. Assuming that the orbit of Earth around the Sun is circular and that one revolution takes 365 days, find the linear speed of Earth in miles per hour.
Thank you so much. First of all, generally speaking, the orbit is elliptical shape. Everybody knows that. But if we assume a circular, but by the way, it's fairly close. As far as getting that 9.29, they basically add up 94.5 and 91.4 divided by 2, and roughly we get 9.29. That's the approximation, and that's distance of the Earth from the Sun, and that distance is the radius. Actually, this distance is the radius. Okay, and one revolution takes 365 days. That is the concept of speed, angular speed. And so let's look at the given. The given is r is 9.29 times 10 to the power of 7. Okay, so we have a revolution per year, then rpy, we have revolution per day, okay, rpd, and then revolution per hour or per minute and so forth. Okay, so obviously, as you can see, we want miles per hour. That's why I don't want to go with rpm, everybody. We go with rph. Understand, h stands for hour, d stands for day, y stands for year, and m stands for the minutes. Now, so one revolution take 365 days. Okay, so we have one revolution divided by 365. Oh, that shouldn't be in that order, class. I'm sorry. For now, you can ignore that. Omega is one revolution in 365 days. Okay, one revolution is 2 pi radians. Okay, and so it's 2 pi radians per 365 days. Okay, and so we change that to hours. So that means we have to divide by 24, and it becomes pi over 12 times 365 radians per hour. I want to make sure you understand why we are keeping it exact. Okay, I don't want to change anything. I just want to simplify what I can. And as you notice, for example, number 2 and number 24 cancel each other, and that's how we get the 12. Okay, class? And the reason I do that, generally speaking, when you want to do any calculation, you want to keep your approximation out of the way until the very end in order to have a better approximation. Otherwise, you get to what is known as round off error. You keep on rounding and rounding, and by the time you get to the answer, you have rounded so much that it's way off. So the thing is, we just changed this to we changed it to radians per hour. And the reason we kept it as hour, because we want to go to miles per hour. So if we use the fact that linear velocity is r omega, okay, so I'm going to quickly recap because that came first and it wasn't supposed to, okay. First, we calculated omega. Angular velocity was given. When we say 1 revolution, that means 2 pi radians, takes 365 days. So how many revolutions per day? 2 pi divided by 365. Okay, I want to make sure I write this so everybody understands what we mean here. This is the same as writing 2 pi over 365 radians per day. That is our angular velocity per day. We're going to change it to per hour. Basically divide by 24. That's really the bottom line, okay? All right, so that gives us pi over 12 times 365. And when we multiply those, we get 9.29 times 10 to the power of 7. Okay, that's miles, okay, class, okay, and times pi over 12 times 365 radians per hour. So let's put it back in. 9.29 times 10 to the power of 7 times pi over 12 times 365. That should be meters, 9.29 times 10 to the power of 7 meters, I think, because I'm looking at 1 mile being 1609. Okay, so the meters cancel each other here. And we get, let me see what's going on here. I want to make sure 9.29 times 10 to the power of 7. Okay, that's the radius we're going to use. Okay, and what else do we have here? Radians per hour. Okay, so that is miles per hour. Okay, so this ends up being 66,633 miles per hour. The number sounds about right as far as I remember. But let's see. Let's see if we can quickly do a few questions. Could somebody read that one for us, please?
Yeah, sure. Two
Thanks.
pulleys with one radius 2 inches and the other with radius 8 inches are connected by a belt. See the figure. If the 2-inch pulley is caused to rotate at 3 revolutions per minute, determine the revolutions per minute of the 8-inch pulley. Hint, the linear speeds of the pulleys are the same, both equal the speed of the belt.
Thank you so much. So that is the fact in physics that we are going to use. So obviously, we can see the radii. One of them is 8, one of them is 2. That's not a big deal. Okay, so that's given. And then the 3 revolutions, okay, that means RPM. So we have 6 pi radians per minute. Basically, those are given. So as we read the question, we notice those are the given. I can't emphasize this enough. Now, also, the hint tells us their linear speeds are the same. That means they have the same V. V is R omega. So V1 and V2 must be the same. R1 omega 1 must be equal to R2 omega 2. The reason we are using the subscripts because now we are dealing with two different pulleys with different radii. So we plug in the radius for each, okay, and we find omega sub 2, which is missing. So omega 1, okay, because the 2-inch pulley gives us 3 revolutions. Okay, class? So that's why we call it omega 1. In other words, it pertains to this one. And so cross product gives us 12 pi over 8, okay, radians per minute, and that's 3/4 of a revolution per minute. Understand why we are changing it, because it was given as revolutions per minute for the first one. We are going to give it back in the same format, RPM. Remember, omega is 2 pi RPM. So you have to divide it by 2 pi to get to the different units of revolutions per minute. All right. Sounds good, class?
Yes.
Perfect. All right, could somebody read this question for us? I'm hoping we get to finish at least this section. I appreciate if somebody reads this fast for us, please.
Earth rotates on an axis through its poles. The distance from the axis to a location on Earth 40 degrees north latitude is about 3,033.5 miles. Therefore, a location on Earth at 40 degrees north latitude is spinning on a circle of radius 3,033.5 miles. Compute the linear speed on the surface of Earth at 40 degrees north latitude.
Thank you so much. Understand that at that point, this is the radius. We are really looking at V equals R omega. And what is the omega? Okay. 1 revolution per day, a complete revolution, 1 day. Okay, 1 revolution per day. And that's 2 pi radians per day. Each day is 24 hours. I haven't shown this work because I think by now we are used to it. So one more time, 2 pi radians per day. A day is 24 hours. So 2 pi radian divided by 24 is pi over 12 radians per hour. V equals R omega. And R, we have it as 3,033.5 miles. And that gives us the speed. Now, I want you to know that that 40 degrees north latitude is a piece of information that doesn't come to calculation class, okay? And so what comes to calculation is that at that latitude, there appears to be a different radius that we have to deal with. That's really the point of this question, the radius that we use at. Sounds good, everybody?
Yeah.
I really want to go over 2 more questions fairly fast. I hope you see why I want to do that. I want you to be exposed to all types of questions. And ultimately, all of them use 2 important things, linear velocity and angular velocity. Linear velocity V equals R omega or S over T. And angular velocity is total angle over total time, theta over T, okay? or 2 pi times something such as RPM or RPS or RPD and so on. So here's the next one, everybody. Could somebody read this question?
To approximate the speed of the current of a river, a circular paddle wheel with radius 4 feet is lowered into the water. If the current causes the wheel to rotate at a speed of 10 revolutions per minute, what is the speed of the current in miles per hour?
Thanks. Think about the practicality of this. If we want to measure the speed of the current, this is one way to do that, okay? I hope you find these questions interesting. So what is given? The radius is given and omega is given. Omega is 10 RPM. So 10 revolutions per minute. You multiply it by 2 pi. So omega is given in RPM. You change it to radians per minute. Now, what about V? V equals R omega, as always. And so you plug it in and it gives you 80 pi feet per minute. So what we want to do, feet per minute. We want to go with, to make it miles per hour. So we need to put appropriate unit transformation such that the ultimate answer is miles per hour. Again, we've been exposed to this. We should know this. And we say 1 mile is the same as 5,280 feet in any order, but you have to figure out the proper order. Notice they cancel each other. They cancel each other. And again, I have skipped a couple of steps here and there. You can do the calculation. Don't forget there's a pi 80 times pi times 60 divided by 5280. It's about 2.86, close to 3 miles per hour. That's the speed of the current. Okay, class? I will get the last question. I don't want to miss that, class. Before I do that, is everybody okay with this?
Yeah.
Yes.
Perfect. I really can't emphasize this enough. We had a lot of applications here. I hope you spend enough time to really get comfortable with those, okay? Could somebody read this question for us?
A Ferris wheel whose radius is 30 feet takes 70 seconds for 1 revolution. What is the linear speed in feet per seconds of this Ferris wheel? What is the angular speed in radians per second?
Thank you so much. Okay, so as you can see here, the radius is given, right, class? It takes 70 seconds, okay, for 1 revolution. So really, omega is given in essence, and that means 1 revolution per 70 seconds. Now you want to change it to radians per second. So, which means you can calculate, okay, the R is given, okay. The omega is given as revolution per 70 seconds. 1 revolution per 70 seconds. So you're going to multiply it by 2 pi, and it becomes 2 pi over 70 seconds, radians per second. It's important to know the units are, let's just cross this out and write down, the units are radians per second now. Okay, class? Radians per second. And radian, you know, when you combine it with other units, really it goes away. It doesn't mean anything in that sense. But the way it's given, just radians per second. V, of course, is R omega. Just plug in R omega. (30 times). Now 2 pi over 70 is the same as pi over 35 because number 2 and number 70, they can cancel each other, class, okay? Number 2 can go away. Number 70 becomes 35. That's how we get pi over 35. And this is really radians per second, okay? Now we want to change this to feet per second, okay? So this is 6 pi divided by 7 seconds, and it becomes 2.69 feet per second. And understand, the units of radians has no effect. 30 was in feet, so you can actually say 30 feet, okay? So 30 feet, so the units are feet per second as the final answer. Any questions, class?